So in this video, we're going to look at a quality of atoms called electronegativity that's hopefully going to help us understand why some combinations of elements will form ionic compounds and other combinations of elements will form molecular or covalent compounds. So when we have two identical atoms that are nonmetals, that they come together and share electrons, the electrons are going to be shared exactly halfway between each atom in the covalent bond. So when those two hydrogen atoms come together and they share a pair of electrons, the electrons don't lie closer to one atom or the other, they sit exactly halfway between the two atoms. However, most covalent bonds involve different types of atoms that have different tendency to pull electrons towards themselves, and as a result, most of the time electrons are not shared equally in covalent bonds. So if I look at the molecule HCl, what I'll find is that the electrons lie a lot closer to the chlorine atom than they do the hydrogen atom. They are not shared equally at all, and this gives rise to what we call a polar covalent bond. When we say that something is polar, we mean that it has a more positive end and a more negative end. So in this case, we can indicate that by in this case, the electrons are pulled closer to the chlorine, so the hydrogen end of the molecule is more positive, and we can indicate that by writing a delta, which is I just write an S and close the bottom loop, a delta, and then indicating that plus, that means it's a little bit positive by the hydrogen, and then we write a delta and a minus near the chlorine to indicate that the chlorine end of the bond is a little bit negative. Now, there is another way of labeling that we have this unequal sharing of electrons, and that's with what we call a polar arrow, and we draw an arrow pointing towards the more negative end of the bond, and then we turn the more positive end of the bond into a plus sign. So in this case, we say that the bond is what we call a dipole. It has a positive pole and a negative pole. It has two poles to it, a positive end and a negative end. So many covalent bonds will be what we call polar covalent bonds because of this tendency of one atom to pull electrons towards itself more strongly than the other atom. So we can predict which pairs of atoms will form polar covalent bonds with uneven sharing of electrons using the periodic table. And the reason is because there is an increasing tendency to pull shared electrons towards itself as we move from the bottom left to the top right of the periodic table. So fluorine really rips those electrons in towards itself, those ones that are being shared, and hydrogen, it doesn't really do that very much at all. So this is just a periodic trend. Can we give some numbers to it? Well, there have been a lot of systems that have been devised to try and give some numbers to this property, which is called electronegativity, for each of the elements, and the most famous one is that developed by Linus Pauling. So electronegativity is the tendency of an atom to pull shared electrons towards itself, often abbreviated with the symbol uppercase E, uppercase N. And Linus Pauling developed a system where he gave every number in the periodic table an electronegativity value. The highest value is 4, that's for fluorine. Okay, so they range from 0 to 4. Now, Linus Pauling is an interesting guy because he's the only person to independently win 2 Nobel Prizes in 2 different disciplines. So I think he got the Peace Prize and also the Chemistry Prize, and he did it all by himself. Often Nobel Prizes go to teams of people. He actually comes from the Pacific Northwest, and he was educated in Oregon, and what's interesting about Linus Pauling was he was a really outstanding student during his undergraduate career and during high school, but he really didn't like taking those humanities and social science credits, and he was actually allowed to move on into the university even though he hadn't finished off his high school diploma. And then I think similar again, they kind of just cracked and gave him his bachelor's degree even though he didn't quite complete all of the requirements because he was an amazing science student. So here are Pauling's values for electronegativity. As I said, the highest value is 4 for fluorine, and then they go, the noble gases don't really form bonds, so they are either assigned a value of 0 or undefined, I think is one way that sometimes people put it. But the general trend is that they increase in value from the bottom left to the top right. Now, it is worth keeping in mind that the elements that we're really going to be applying this to are the non-metals, which are just these guys over here, because we're going to be using this to understand covalent bonding. Now, we can also use it to a certain degree to understand ionic bonding. So when we think about bonding, we can think about it now in terms of the difference in electronegativities between the atoms that are being bonded. So if we have two identical atoms with no difference in electronegativity, we have what we call pure covalent bonding. The electrons are going to sit exactly halfway between the two atoms that are sharing those electrons, and that bond will have not a positive end, it won't have a positive end and a negative end. We'll have what we call pure covalent bonding. Now, if we have sort of like modest differences in electronegativity, maybe what we saw with hydrogen and chlorine, and we have unequal sharing of electrons, we get what we call polar covalent bonds, where our bond has a more positive end and a more negative end. Now, if we have really, really big differences in electronegativity, like say between a metal and a non-metal, right, because all the metals have really low electronegativities and the non-metals all have really high electronegativities, then we don't just get unequal sharing of electrons, we get complete transfer of the electron. So here we go, there's not any sharing here, the electron just goes straight on over. It gets ripped off by the more electronegative element, by the non-metal, and that leaves us with a cation and an anion, right? So if the difference of electronegativity is big enough, then we get transfer of electrons, and we end up with what's called ionic bonding. So how do we know on the basis of electronegativity values what's going to happen? Well, generally, if the difference in electronegativity is less than about 0.4, then we're going to have, pretty equal sharing of electrons, and we won't really observe any kind of like obvious effect of the bond being polar in any way. So, once we get above a difference in electronegativity of 0.4, then the polarity of that bond starts to have real world consequences, and we'll see some effect in the properties of our compound. Now, if we get above a difference in electronegativity of 1.8, then we no longer have sharing of electrons. We have complete transfer of electrons to the more electronegative element. So, let's have a look at some Alex type problems. So we have to reorder each of these lists of elements in order of decreasing electronegativity. So electronegativity decreases from the top right to the bottom left of the periodic table. And so the elements in the first part of the problem here are all halogens in group 7A. So we got chlorine, bromine, and iodine. And electronegativity decreases as we go down a group and from right to left across a period. So we need to list these, if it's in order of decreasing electronegativity, in the order of them going down the group. So chlorine is going to have bigger electronegativity than bromine, which will have bigger electronegativity than iodine. And we can see that in our numbered periodic table here. Okay, so now we've got oxygen, boron, fluorine. So oxygen, boron, fluorine. And we see that they are all in the same period. And we know that electronegativity decreases as we move to the left across a period. So it's going to need to go fluorine is greater than oxygen, which is greater than boron, and we can see that in our table. It goes 4, 3.5, 2.0. So if you've got the information available to you, answering these ALEX type problems is really straightforward. The key thing is good notes and making sure that you've got the resources that you need to hand. Okay, so this problem is all about predicting bond polarity. So what are we going to do? We're going to look at the two atoms that are in the bond, and we're going to then look at the electronegativities of those atoms in the periodic table and decide, is there unequal sharing of electrons, and if so, what is the more electronegative atom? So we have two options for each case. It says the highlighted bond is polar and the more negative atom is, or alternatively we can say that the highlighted bond is non-polar. Now this bond is between two carbon atoms, so the difference in electronegativity is 0, right? Because both of those carbon atoms have an electronegativity of 2.5. The highlighted bond, so that is non-polar, that bond. The highlighted bond in this case is between a nitrogen atom and a hydrogen atom. So nitrogen is over here, it's got electronegativity of 3, and then hydrogen is over here, it's got electronegativity of 2.1. So in this case, we've got a difference in electronegativity of 0.9. So that's a polar bond, right? So it is polar. And the more electronegative atom, the more negative atom, is going to be the nitrogen atom. Okay. All right. So now we've got hydrogen and bromine. So bromine is over here. Hydrogen is over in group 1A. So the difference in electronegativity, 2.8 minus 2.1 is 0.7. So that's going to be a polar covalent bond. So that bond is polar, and the more electronegative atom is going to be the bromine. So pretty straightforward, right? If you've got two different atoms, it's going to be a polar covalent bond, and if you've got two of the same atom, it's going to be non-polar. Now some of the elements coincidentally have the same electronegativity, so you can see a bunch of the group 1A metals over there, and then if we go over here we can see boron and germanium, we can see nitrogen and chlorine have the same electronegativity. We can see carbon and sulfur have the same electronegativity. So you do want to check it against the values just to be certain. Okay, so that concludes this video on electronegativity. I hope you found the video helpful.